All right, so Galileo's inclined plane experiment. Now, this particular handout I've been using for a lot of years. You'll notice on the bottom of the page there, 2003 I first printed it. Okay? And what this is a write-up from some students at a university, and they basically reenacted Galileo's lab. So they say, using equipment that we might now call simple or even rudimentary, Galileo revolutionized basic scientific principles which were posited by Aristotle and held firmly by scholars of the High Middle Ages and the Renaissance. What do you think the word positive means? Not proven, though. Proposed, good synonym there. Proposed or suggested by Aristotle. And unfortunately, no one sort of bothered to check up on Aristotle, and he was wrong, and people believed him for about 2,000 years. I often wonder when I get to this part of the course, what stage would our human civilization be at if we hadn't listened to Aristotle for 2,000 years? We'd be certainly more advanced. I also wonder if maybe people did sort of disagree with him, but perhaps they were taken care of. Let's leave it at that. They were discouraged from suggesting that Aristotle was wrong. It goes on to say, one of his most important experiments was the inclined plane experiment. Galileo used his inclined plane, a simple board with a groove down which he rolled a small metal ball to examine Aristotelian ideas about motion. Very similar to the ramps that we used, right? With a rolling ball rolling down. Galileo's inclined plane experiment radically changed these ideas by concentrating on acceleration, the stage of motion ignored by Aristotle and most of his followers. Aristotle, to be honest, I don't even know if he believed in acceleration. Kind of weird. We decided to, so this is the students again, still speaking, we decided to replicate Galileo's inclined plane experiment because it was so fundamental to new concepts of motion in Galileo's time. We based our experiment on Galileo's own description of the inclined plane in his book, Discourses on Two New Sciences, published in 1638. So this is taken from the book. These are Newton's words translated to English. A piece of wooden molding or scantling about 12 units or 7 meters long, half a cubit about 30 centimeters wide and 3 finger breadths or 5 centimeters thick was taken, and on its edge was cut a channel a little more than 1 finger in breadth. And having made this groove very straight, smooth and polished, and having lined it with parchment, also as smooth and polished as possible, we rolled along in a hard, smooth, and very round bronze ball. So he took a piece of wood, put it on its edge, put a groove down it, made it nice and smooth, and rolled the ball down to the edge of it. Okay? So these are the students' words now. Our own construction entailed planing at a 45-degree angle, one edge each on two 16-foot 2x4s, which when nailed together formed a groove. We sanded and oiled the groove to create a low friction effect, like Galileo's parchment. Instead of a small bronze ball, we used a 3/4-inch steel ball bearing. We added a metal piece to the end of the inclined plane, against which the ball struck at the end of each run to make our timing precise. Click here for a more detailed description. So they took two 2x4s, sort of cut off the corner, and then nailed them together and kind of created a V kind of shape. And then they smoothed it, oiled it, made it really, really smooth. We also replicated Galileo's apparatus for timing the inclined plane. Galileo describes his water clock in Discourses on Two New Sciences. So this is, again, Galileo's words. For the measurement of time, we employed a large vessel of water placed in an elevated position. To the bottom of this vessel was soldered a pipe of small diameter, giving a thin jet of water, which we collected in a small glass during the time of each descent. The water thus collected was weighed after each descent on a very accurate balance. The difference in ratios of these weights gave us the differences in ratios of the time. So in Galileo's time in the 1600s, they didn't have iPhones, they didn't have stopwatches, they measured time by sundial. Pretty tough to measure seconds with a sundial. They probably had hour glasses, but they would just measure how long an hour is, right? They can't measure a minute or a second or certainly anything like that. Second, you'd be doing this all the time, right? Really wouldn't be very accurate. So what Galileo did was he used a big bucket of water. And instead of measuring his time in seconds, he was measuring the time in amount of water. Okay? And then he weighed the water. And well, obviously longer periods of time just simply meant more water. Right? Pretty smart, actually. So, back to the students. They did this. Our water clock consisted of a plastic bucket with a small hole drilled in the bottom into which we placed a length of plastic tubing. When filled with water, the bucket emitted a thin stream of water through the plastic tubing. We controlled the flow of water by clamping the tubing with a small metal clamp. We marked our inclined plane at 1/4, 1/2, and 3/4 its length. Starting with the full length of the plane, we rolled the ball 20 times down each length, timing each trial with our water clock. Like Galileo, we weighed the water in each trial so as to determine the ratio of the times for each length. Now, you might expect that the full distance would take a certain amount of water, half the distance would take half. Most people would think of that. You'd be wrong. How come? Because the ball is going faster and faster. That's why. Okay? So really the point of the Reich students, the university students, was for this. Our experiment proved that Galileo could have attained the accuracy which he claimed with his experiment. Our findings also point clearly to the concept of acceleration. The ball travels down 1/4 of the plane in half the time it takes to traverse the entire plane. The first quarter takes half the time. The next 3/4 only take the other half. How come? It's going faster at the bottom. Aristotle would have posited, of course, that the ball's time would be directly proportional to the distance traveled. Twice as far, twice as much time. Andrew Irving has created graphs which clarify Galileo's discovery that the ratio of the distances traveled traversed by the ball is proportional to the ratio of the squares that happen. I'll explain a little bit more about what that means. So that's just really a description of Galileo's experiment. Okay, can you find this sheet, please? Because this sheet's important. Okay? So, I think actually, if I'm not mistaken, I think it's tomorrow that we start this class. So pay close attention, because you're going to be creating a table much like this tomorrow. Okay? So let's just have a look at the top here. How far does the ball go? How far does the ball go in the first second? Where does it start? It starts at 0 and it ends up at 0.5. So how far did it go in the first second? 0.5. How far did it go, or where is it at the end of 2 seconds?
2.
It's at 2. How far does it go during that amount of time? Goes in that 1 second. It went 1.5, didn't it? How far does it go in the next one? 2.5. How far does it go in the next one? 3.5. It goes farther and farther each time. How come? Because the ball's accelerating, just like the yellow car in the notes from the other day, right? The distances between them get farther and farther and farther. Okay, so now let's look at the table at the bottom here, okay? So all of these intervals are numbered. All of these intervals are numbered, just 1, 2, 3, 4, 5, no big deal. What's the time at the very start of the first interval? 0. What's the time at the end of the first 1 second interval? 1. What's the time at the start of the second interval? Also 1, right? And it ends up at 2 seconds. And then the start of the next interval is at 2, and so on. And do you see how this pattern sort of exists here like this? Right? The time at the end of the previous interval is the time at the start of the next one. Does that make sense? Give me the nod of understanding. Okay? The time at the end of the interval is the time at the start of the next one. Okay, so how long is each one of these intervals? Each one of these intervals is 1 second, right? Okay, now let's talk about position. Where do we start the whole experiment at? What position? 0. Where do we end up at the end of the first interval? 0.5. If I started at 0 and I ended up at 0.5, how far do I go? 0.5. Now, if I ended the last interval at 0.5, where do I start the next interval at? Also 0.5. There's that pattern again, right? And I end the second, I'm at where? Position 2. If I started at 0.5 and I ended at 2, how far do I go? 1.5. And if I ended the last one at 2, where do I start the next one at? 2. And then I end up at 4.5, so I go a distance of 2.5. And if I ended up at 4.5, where do I start the next one? 4.5. And if I ended at 8, then I start the next one at 8, and so on. Give me the nod of understanding. No, wakey. Okay, you will notice that the distance traveled is going up by how much? 1. It's going up by 1 meter each time. It's going 1 meter farther than it did in the last second. Okay? Yeah? Okay. Now, Let's talk about the velocity. If I went 0.5 meters and my interval is 1 second, I want you to write this right here. V bar is equal to d over t. How far did I go in this interval? 0.5. How long did it take? 1 second. 0.5 divided by 1 is an average velocity of 0.5. Pay attention here. If I went a total distance of 1.5 in 1 second, what's my average velocity? 1.5. If I went a distance of 2.5 in 1 second, then I've got an average velocity of 2.5. If I went 3.5 meters in a second, I was going 3.5 meters per second. If I went 4.5 meters in 1 second, I went 4.5 meters per second. What do you notice about the average velocities? Also, going up by 1. How come? It's going faster and faster. Okay, here's where it gets even crazier. Watch closely. You're going to have to do this tomorrow. Okay? You can't say tomorrow, you didn't show us how to do that. I'm showing you today. How fast is it going right at the very start? 0. It's at rest. Now, if I started at 0 and I averaged 0.5, how fast do I have to be going at the start, at the end? If I start at 0, Noah, and I average 0.5, how fast am I going at the end? 1. The average of 0 and 1 is 0.5. In fact, this 0.5 is exactly in the middle. That's what average means, right? If you got 0 on one test and 100 on the other, what's your average? 50. Now, if I'm going 1 meter per second at the end of the interval, how fast am I going at the start of the next one? Also 1. And if I started at 1 and I average 1.5, how fast am I going at the end? 2. What's the average of 1 and 2? 1.5. And if I ended this interval at 2 meters per second, what do I start the next one at? Also 2. And if I started at 2 and I average 2.5, then I have to be ending up going 3. I see some people starting to nod off here. Watch. You have to do this tomorrow on your own. If I end the interval at 3, what do I start the next interval at? 3. And if I started at 3 and I average 3.5, what do I have to end at? 4, because the average of 3 and 4 is 3.5. T, give Josh a nudge there. He's nodding off. Wakey, wakey. Josh, if I end the interval at 4, what do I start the next interval at? 4. And if I start the interval at 4 and I average 4.5, what do I have to end the interval at? 5. The average of 4 and 5 is 4.5. And so you will notice again that what's happening to the instantaneous velocities? They are going up by 1 meter per second every second, which is an average acceleration of 1 meter per second squared. How would I make the average acceleration a bigger number? What would I have to do to the ramp? Make it steeper. Exactly, right? Why is this number always the same? Because the ramp is straight, right? It's speeding up by the same amount each time because it's straight. Is this always going to be 1? No. Will it always be the same? As long as the ball is rolling down a straight ramp. Okay, so back to the video from the other day. I'm going to stop it and I'm going to explain little bits and pieces as we go here. Remember now, so we're looking at this acceleration time graph here. Ray, what are you doing, man? What kind of graph is this? This is a graph of velocity. So it shows the velocity. That's what a graph of velocity time is, right? So how do you do this first print? What is the velocity at 0 seconds? 1. What is the velocity at 2 seconds? 2. What is the velocity at 5 seconds? 3.5. What is the velocity at 10 seconds? Brayden, you should watch this now so that I don't have to explain it. No, you're not. You're doing your binder. Put the stuff down. What is the velocity at 10 seconds? 6. Okay, now you will notice that the acceleration column kind of doesn't line up. There's a reason for that, right? Acceleration is the change in the velocity. How much does the velocity change here? It's going to be 2 minus 1. Goes from 1 to 2. 2 minus 1. How much time did it take? 2 seconds. 2 minus 0, so it's 1 over 2, or 0.5. 0.5 what? Meters per second squared. That's the unit for the slope here. Okay, what's the next one? The acceleration. It goes from 2 to 3.5. So I'm going to go 3.5 minus 2 all over 5 minus 2. 3.5 minus 2 is 1.5, and 5 minus 2 is 3, and 1.5 divided by 3 is 0.5 meters per second squared. And what about the last one? How much does the velocity change from 3.5 to 6.5? 6.5 minus 3.5 is 3. And how much time did it take from 5 to 10? Oh, hang on. This is just 6, right? What did I do wrong there? 6, yes. This is just 6, right? Thank you. This is just 6. So 6 minus 3.5, right? Is a distance of, a change of 2.5. 10 minus 5 is 5. And once again, 2.5 divided by 5 is 0.5 meters per second squared. Why are the accelerations all the same? Because it's a straight line. And what is the slope of this line? 0.5. Why is the slope 0.5? Because the slope of the VT graph is equal to the acceleration. The slope of the VT graph is acceleration. This line stays straight, and so the acceleration remains at 0.5. Now, on the back side, does the velocity remain the same all the time? Or does the slope remain the same all the time? It does not. So are you going to get the same acceleration all the time? No, you are not. Okay, so if you haven't completed that, please do so. If you haven't completed the ones on the bottom, please do so. If you are completely out of things to do, this, Brayden, okay, thank you. If you are completely out, here is, I have lots of these, so this tells me that not everyone got one of these. So if you have nothing to do, you can work on this as extra practice. Tomorrow, I'm moving on. If you're finished this one, then you find something to do. Okay? Tomorrow, I'm moving on. This has got to be the last day of these sort of cleanup stuff. Okay? I'm going to check and see who hasn't turned in rolling ball lab. Okay? So hopefully you've got that in as well. Here. Question. Tell me what? Because of shaking? Yeah. You know what? How about? Yeah. I guess. You know what? How about we flip it upside down and have a look at the problem? All it is tightening. So you guys flip it up on it. Go now. Okay, so you guys should all know what you're doing. Get it done. Don't stop until it's done. Okay, so today Your job is to get that done. Understand? Done. Finito. I don't care where you do it, just get it done. Okay, turn around. This is not you. Get it done. Stop visiting. Too much visiting. Okay, you're not, please, what's your next period class? I understand. Mr. Dick, okay. I need that done today, okay? I don't understand why working over there you think is better. Yeah, Mike, because part of it is like, a non, like, it's like, you go downstairs. Press it.
Somebody's been calling us.
Keep going, man. It's just a table. You can put it upside down. Get this done. Come on, get it done. Keep trying. I expect you. What do you do? I'm making sure you get the work done. Okay, goodbye. Goodbye, better. What?